Hi, I'm Wei Gong. I'm a professor at the University of Massachusetts Amherst. Today, we are interviewing Professor Larry Ho for the IEEE History Project. Professor Ho is a titan in the field of control theory and applications. His research spans over 5 decades and has profound impact on optimal control, differential game theory, discrete event dynamic systems, and ordinal optimization. With me are Professor John Bellio and Hua Wang of Boston University. John is a leader in the IEEE control system community. John and I were both graduate students at Harvard University, where John's advisor Roger Brackett and my advisor Larry Ho led a small and good group in which we benefited greatly from their teaching. Now let's start. So we first talk about the genesis of a control theoretist. Professor Ho, you entered the field of control theory during what many consider its golden age in the later 1950s and 60s. What initially drew you to systems and control out of all the disciplines emerging at that time?
Oh, that's somewhat of a long story, but I should back up to the beginning. I grew up in China and spent the first 15 years of my life during World War II, where the Japanese-Chinese War was going on. So the Japanese occupied gradually about half of China geographically. So my father was working for the Chinese government, so I had to move around. I went to 5 different elementary schools in the first 6 years, and including 1 year I was sick with typhoid fever, so missed the school entirely. That gives you some idea how somewhat chaotic my early life is. Then, after World War II, the family returned to my original birthplace, Shanghai, where I didn't quite finish my high school. I finished 11th grade. Then the communists came, and since my parents worked for the government, a nationalist government, they had to leave. So I was sent away from home to Hong Kong in a British boarding school and finished my high school there. And then I came to the United States at age 16, alone, without assets, without friends, except the promise of education. So I went there for the next 76 years until today. I live in the United States, and basically around Greater Boston area.
Why did you choose the system and control?
Oh, yes. Again, that's an interesting story. When I was at the British boarding school in Hong Kong, somebody came back from studying in the United States and stopped by, and he talked to me about, I went to MIT. At that time, I began to show some aptitude in science and math, and heard about MIT. So on my own, I wrote a letter of inquiry to MIT. Immediately came back with a lot of material, including application form. So I filled it out and sent it in, and to everyone's surprise, including my own, I was admitted to MIT. So I came to this country at age 16, alone, no friends, but had a great start at MIT.
At 16?
15, yeah, because of the way Chinese, and to some extent, Chinese still count age. When you're born, you're 1 year old because you've been alive for 9 months in your mother's womb. And after New Year's, you add 1 more year. I was born in late November, almost the end of November, according to the lunar calendar. But that was already, the Western New Year is already over. The Chinese New Year is 1 month later. So after 1 month, I was 2 years old. And I entered college at the Chinese age of 18, which is really I'm only 60.
Right.
So that's the background, yeah.
John, you want to ask a question about significant events in the early days, childhood?
Well, yeah, I mean, very interesting history that, you did so well because, it was a time of turmoil and so forth in China from different sources, not just the war. And, but you got it, as you correctly said, I mean, very interesting that you had a knack for things that were technical, mathematical, and scientific. And you ended up at MIT, which was great. And what did you set out to study when you went to MIT?
Yeah, that's also an interesting story. When I was growing up in our attic at home, there was a very old European ornamental clock that has a mechanism that a bird would, artificial bird will come out of the door, opens, all part of the clock, and will chirp every half an hour or an hour. And it's not working. So I got hold of it and looked at it, slowly figured out what was wrong, and restored the clock to a working order. Everybody was surprised. So that determined, so you should study mechanical engineering because that's what I'm good at. And so when I applied to MIT, they admitted me, but made a mistake, which says I was admitted to the EE department, electrical engineering, for a reason I don't understand. But anyway, at that time, first year, for all entering freshmen, they study the same thing. It doesn't really matter what department you're supposed to major in. But since I was in the EE department by mistake, when I actually applied for mechanical engineering, I got invited to all kinds of seminars, events, to familiarize the freshmen with the institution. So I got used to EE, and that became my field. And they are amazing. It really doesn't matter what you study.
Very good.
I went to work after the graduate. And what I was working on was digital computer, which I never studied as a graduate, but it doesn't matter. You learn.
Yeah.
And then when I came back to school for my graduate study, what I did has very little to do with what I learned in industry. And then when I finally got promoted to tenure at Harvard, what I did to get my promotion had very little to do with what I learned while in graduate study. And so you always have to learn new things.
Yeah. That's very interesting, and that's actually very much related to my next question. As during your early years at Harvard, the transition from classical frequency domain methods to state space and optimal control was rapidly unfolding. What was the atmosphere like among researchers as those massive paradigm shifts were happening in real time?
Yes, I always say I was born in the right year. So when I was beginning my graduate study, well, I should mention, I'm going to mention things which nowadays we consider quite unacceptable politically and so forth. But at that time was quite normal, done with perfectly good intentions. And so a lot of things I said should not be considered as disparaging or anything that happened at that time. All these things were very normal. And remind me the
question that's the transition in control theory.
Oh, yes.
From classical control theory to
yes, right. That time, I would say, as I was born in the right year, so when I began my study, there's a big revolution in the way we do control. Now, MIT at that time was still resting on their World War II success. The Rad Lab series of books was published, and in fact, if you study control, people say there's only 2 books you need to know. One is nowadays you don't even hear about them now, but that time was considered the most important book in control by Bodie, Feedback Amplifier Design, and another is The Theory of Servo Mechanism by Brian Campbell. The story at MIT. If you know these 2 books, you don't have to know anything else. Everything's there. But nowadays, most students probably never heard of these books. They're completely changed. And that is, of course, due to, I think, without question, the father of the revolution that took place in late 50s, early 60s.
Yeah. Wait. Yeah. So maybe I can just ask, though, this is a good point maybe to ask the question about how you decided to move from MIT to...
Yes. Okay. I did quite well at MIT, undergraduate. Then I have to go out. I need money, I go out to work. And I learned all about digital computers in the late 50s. That's just coming into fashion. Then when I want to come back to MIT, and I don't mean to cast dispersion on this, there was a quota on the number of Chinese students of Chinese ethnicity that can be admitted to the EE department at that time. Now, I mean, this sounds so unusual nowadays, but at that time it's very normal. I have exceeded the quota, so MIT would not send me an application form for apply for admission, because if it did, I had a very good undergraduate record, and other departments will question, say, this is your own student, has a good record, why do you want to deny him? So they just never bothered to send me an application form. I went to my second choice, Harvard University, which turned out to be a blessing in disguise.
So, and maybe you could just reflect on the people you interacted with.
Okay.
I actually know your thesis advisor, but...
Yeah. At that time, Harvard actually had no competence in what is the revolution that's taking place with President Rudolf Kalman as basically commonly acknowledged as the father of the revolution. By the way, this is a little unknown. He was an undergraduate 3 years ahead of me at MIT, Kalman.
Yeah.
And when I was an undergraduate, he was already in graduate school. Yeah. And he did a very interesting master thesis, and the department actually let him give a seminar, which is unprecedented. But Kalman has a rather straightforward, brute force personality. He used to tell his professor, "You're wrong, I'm right. You're just not smart enough to know that you're wrong." I mean, that did not endear him to anybody in the department. And when he took his qualifying oral, they wanted to teach him a lesson and just flunked him. And I later on got to know him well, so he told me this personally. He said, "I just flipped the table, said, you made the biggest mistake in the department," and left MIT. And he told me he drove 3 days and nights all the way to Caltech, asking Caltech, said, "I'm great, admit me to your Ph.D. program." Of course, they said, "Who is this? An unknown student from somewhere who just flunked out of MIT." So they didn't. And so he had nowhere to go, so he had to accept a job at DuPont Chemical. And it turns out the Dean of Engineering at Columbia, a person by the name of John Ragazzini, was consulting for DuPont and recognized the talent of Kalman and says, "Okay, why don't you come to Columbia to do your Ph.D.?" So he did, and that's where he, again, almost failed because of his personality, not because of his smartness. He got his Ph.D., and I got to know him at that time because when I came back to study for my graduate school, there was no competence at all at Harvard. But there's one professor by the name of Bryson, who was a fluid dynamicist. he happened, because of his consulting, he had working with Raytheon about space trajectory for space vehicles. At that time, 1958, the first space satellite called Sputnik by Russia went up, and everybody was surprised. And the U.S. attempt to catch up crashed and burned on the launching pad. Everybody was in a big panic, says we're going to lose the space race. Okay, and that was the time Bryson wrote a paper which most people don't know now because they refer to something else. He and his doctoral student did a paper on what's the minimum time to climb to a certain altitude by a rocket. And that theoretical paper was actually verified because Bryson was an engineer. They actually experimentally verified his results, and that got a big boom. People said, well, this is the thing we got to study. And Rudolf Kalman was right there at the right time. And so it took us totally revolution in the field. While MIT was still resting on the World War II success with the engineering invented frequency, so-called frequency response method. Today, nowadays, not even in textbooks anymore. So
interesting. So actually, I think that you wrote an early paper with Rudolf Kalman on the controllability, right?
Yes, that's another interesting story. When Rudolf Kalman started publishing, he wrote a paper based on certain conditioning of linear systems, wrote a paper with a person by the name of Jack Bertrand. So it's called Kalman-Bertrand conditioning. I was a graduate student, and at MIT, there's nobody who guided me. Bryson's paper accomplished wasn't quite known yet. So I looked at this so-called Kalman-Bertrand conditioning on his paper. I said, oh, I discovered that was a simple condition of linear independence in algebra. So I wrote to Kalman about this, and he immediately recognized the connection. He said, oh, let's write a joint paper. And he started to write this paper, which is nowadays still being referenced, called Controllability of Linear Systems, one of the foundational papers with me. And that's how I got to know Kalman, and unofficially got to, let's say, his guidance and so forth, and started on the entire new field. She said, at Harvard, there was nobody else. Only later on, Bryson recognized the importance of what I did, and that we wrote a joint book together.
Controllability is, so fundamental, important, to all the students today that everyone.
Yes. I still get a citation of this paper I wrote with Kalman, and.
So a little bit, you already talked about Kalman and Bryson, and so I also want to mention that if I heard correctly, Kalman himself once mentioned that your explanation of Kalman filtering was the best, better than his own.
True. I mean, like all inventions, you start off with some intuition, lucky guess, and so his original paper, which is the greatest contribution of his life, the Kalman filter used everywhere, was very difficult to read. And when I wrote the controllability paper together with him, I got to know him a little better. So I had an advanced copy of his Kalman filter paper. And I studied it and finally understood what it does. So nowadays I always say I can talk about Kalman filter in a semester course, in a 1-hour lecture, in a 10-minute summary, or even one sentence. And every one of these way of describing his greatest contribution will make sense and be honest, and not gloss over. So yes, I think when he got his equivalent Nobel Prize award for his contribution, he acknowledged two persons. One was his teacher, the great mathematician called Solomon Lefschetz.
Yeah.
The other one was me, because I was the first one who really recognized his contribution and explained it in a way nowadays even high school students can understand what his contribution was.
That's agreed. And you co-authored with this, the Bryson about this very, very long-lasting textbook, Applied Optimal Control, which I still use to teach. It was such a great book. But I want to mention that some AI pioneers, like Jan LeCun, the 2018 Turing Award winner, and also the Paul Werbers, that.
Yeah, Werbers, I know.
They both mentioned in written that your textbook and your lecture, that the Paul Werbers actually attended your lecture.
Yes, correct.
Says that your teaching of this TVBPC, the optimal control algorithm, give them the motivation and clarification of the backpropagation algorithm, which is the cornerstone of today's AI revolution. So much money was made of that algorithm. You comment on that? You remember these people, this sense about your this influence to the backpropagation algorithm?
Yes, again, this is being at the right place at the right time, but I'm blowing my own horn a little bit, so forgive me. There's something called citation. If your paper be referenced by somebody else, it will be recorded in being read. Usually, if your paper be referenced by 1,000 other papers, it's called a citation classic. Yes. Because it's an important paper, a lot of people read it and think it's important for their work and so forth. And when I started at Harvard, after I graduated, started teaching, Bryson also did his fundamental contribution on this work about minimum time to climb for a rocket to a certain altitude. Unfortunately, most people don't realize it was actually experimentally verified for his theoretical contribution. That really gave a big impetus to the government to put money in there so that we can catch up or win the space race. But anyway, Bryson also, when I started at Harvard, Bryson began to recognize that I was interested in his field, and he got interested in his field at the same time. So we joined and taught a course, and I started writing a lecture notes that eventually became our book, which is now, as I mentioned earlier, if your work has been referenced 1,000 times, it's called a citation classic. Our book now has been referenced 44,000 times. So it's really, I'm blowing my own horn. It become a golden standard for the book and for reference. It's still every week, some either ResearchGate or academia will tell me, oh, so-and-so just referenced this book. And it's been translated to Russian and Chinese because they consider that sort of the book that it's standard. It's still really a gold standard, still being taught in schools every day.
Absolutely.
It's still in print.
Yeah, it's still in print, but I no longer get royalties anymore. Apparently, at the time, well, again, at the time, the CD author was Bryson, and he saw he negotiated a terrific contract with the publisher for publishing book week. You just get percentage of the book. We get $1 per person per book sold. And the book was selling for $15. Now the book is selling for over $100, $115, $120 last time I checked. I still get $1 per book. So,
all right. So then in the book you also described, and your next research focus is on differential games. I think you're one of the few pioneers in that area. And what we students call it a two-side control. How did you decide to look into that? Do you think, in the optimal control? Most people didn't.
Yes, well, again, I credit this to being born at the right time in the right place. So the revolution was taking place, as I said, by Kalman, who completely revised what was then considered current techniques in control. He completely revolutionized the field. And I happened to read I was, during the summertime, was consulting for Rand Corporation. At that time, Rand Corporation has Dick Bellman there. Of course, everybody knows him. Right. And before that, there's a person by the name Isaacs, who started this field by himself called differential games. But he had a difficult personality. He never got along with anybody. In particular, he did not get along with Bellman, so he left. But I was doing the summer job at Rand Corporation, came across this thing called differential games. They got me interested. But Isaac himself is a very kind of strange person. He never was aware of any of the work that he controlled. And I recognized, this is actually a two-sided control problem, and that's which started me on developing the different game theory, and which is where I got the credit for a lot of the work there.
Right.
But Isaac is really the guy who started the whole thing.
I remember the video, that time, the small movie that you showed us of this pursuit evasion.
Yes.
It was so interesting, yeah. But the next shift, that in the peak of your research, you are so well-known, well-established, full Harvard professor, and you switched to discrete event dynamic systems. Tell us why and how it happened.
Oh, okay. This is, again, through consulting. Most universities nowadays have allowed the professor 1 day a week to do consulting. It's not work of the university to earn some extra money and so forth. And I did consulting. And through consulting, they keep you honest, because you have to produce to solve real problems people have. Otherwise, you cannot just talk about theory. And through consulting, I came across the problem of manufacturing and other things, practical problems, where you have to make real contributions to solve real problems. Otherwise, why people pay you to be a consultant? So it's really through consulting with practical problems I came across manufacturing problems, which led me to invent the idea of discrete events, dynamic systems, and perturbation analysis, and so forth.
Great. I still remember that in the group meeting that you were pushing us to say that don't tell me this is just random noise. There's got to be some reason you have to look deeper. And so actually that led to your later student to do the optimization on simulation, which some paper was actually cited in the breakthrough of the AlphaGo algorithm, that they actually use the simulation to decide what's the optimal.
Yes. Yeah, that's really my firm belief, that to allow you 1 day a week for consulting is really useful, because you are forced to be, the person who employ you as a consultant want results and keep you honest. You cannot just do theory. You have to produce answer for their real problems, and that keeps you honest and relevant. Most of my good ideas, theoretical ideas of my academic work, came from consulting. Yeah. Because I always like to do a problem I know very little about.
This is also related to your teaching to us that comparing control theory development versus the computer society. That you always say that the computer people have a real thing to program and to check if you're right or not, and not just theorems.
Yes, I think that's correct. I mean, nowadays, control theories, I call it the third stage. That is the start of phase. And people deal more with theory than with real applications. Not everybody consults for industry and so forth,
Right.
but I hardly recommend that.
Yeah.
It's really sources for new ideas.
Right. So, I mean, just to your point,
Yeah.
Art Bryson, as I recall, Fred Abernathy, who you remember,
Yes, sure.
he told me, Bryson was originally hired at Harvard to run a
Fluid mechanics, yeah, exactly.
and I don't know if he needed the money or he just wanted some outside activity. And the way he came to be connected with control is through his consulting.
Exactly. With Raytheon Company, the Ph.D. student wrote a famous paper with him, which is experimentally verified by the Air Force, called minimum time to climb to a certain altitude. Was working for Raytheon. And through Raytheon, his work, that most people have forgotten about that paper because they refer to his textbook jointly co-authored with me now as the gold standard for the reference. But his original contribution really caused a splash.
Yes, this is also related to my next question. Your next shift of the research focus is into ordinal optimization. Can you tell us more about that?
Yeah, I remember that very well. And I can explain what ordinal optimization is. Your goal in life is to find a good solution with high probability, not to find the best solution for sure. Because the second alternative, find the best solution for sure, is very costly. It's going to cost you a lot of work and sometimes with no results. But if you're satisfied with the good enough, with a high probability, which is most what engineers do, even they may not know about the subject of ordinal optimization, most good engineers, for intuition or good guess or so forth, try to get a good enough solution for the real problem that he faces, and that's enough. So, because again, to my consulting, I often face with real problem. And I remember very well, it's one rainy afternoon, I stayed at home, didn't go to work, and thought about this and developed an experimental trial using the then very new software called Excel, which now everybody uses, and developed a simple example. And found out, to my surprise, in fact, I just spent a little bit of time explaining this because everybody can understand. Suppose you have 200 choices of doing something. You don't have time to really investigate every one of these 200 choices because they involve large project, time, money, so forth, to find out what's the best. So you take using your intuition, some very approximate method, order these things. Say, I think this is best. I think this is second best, so forth. Order these 200 alternatives. And you say, oh, I don't want the real best. Anything the top 12, anything the top 6% of the solution is good enough for me. So you use any method, maybe even random choice. Order these 200 choices, the best to worst. Now, and you pick out the top 12 for more careful evaluation. Let me ask you the question, what are the chances using your approximate method or pure guess or even random ordering of 1 through 200? The first 12 contents are actually a true first 12. Yeah, you don't care which one, so long as the first 6% is good enough. You'll be surprised, even if you know nothing about pick a man out from the street, ask him to pick out but randomly top 12. What are the chances he will actually get a real top 12 in the to become. Surprisingly, it's probably a 50-50 he will get it. And if you're an engineer with any kind of intuition experience, your guess is so much better than the other three. You have much higher probability of getting a real, but just investigate this top 12 by some approximate method to get a true top 12, one of the top 12. That was the basic idea of ordinal optimization that I discovered using Excel. But Randy afternoon, I didn't go to work. I remember that very well. And that experiment is still on display. You can try it yourself very easily. So that's how I came on to my last topic.
Very interesting.
Sorry?
The last question.
Yeah.
For this, we are coming to the time. So this interview will be preserved in the IEEE Historical Archive.
Yes.
And many people will watch it, especially younger people. What is your most important piece of advice for the young researchers in control theory and applications? And in general, the advice for the future researchers?
I would say, just based on my own experiences, do what you love to do. Don't worry about, whether this is going to be better for my career or so forth. Just do what you love to do. America is the only place in the world that lets you do this kind of thing. And not have to worry about making a living and so on and so forth, and about what other people may think about this. So do what you enjoy doing, and don't worry about fame and fortune and so forth. That will come or not come naturally. And if you make that your ultimate reward, then it's not a good thing. But always be prepared for doing what you enjoy doing. That's my one piece of advice.
I think Liza might want to ask a question about the evolution of the applied math at Harvard.
Yeah, I mean, you just from the, the school has changed over the years, and you've been around for a lot of those changes.
Yeah, 46 years.
But I don't know, how did the school change during your tenure there?
Well, I think the greatness of Harvard is they give you a lot of freedom to do things. At any one time, they may be incompetent or have no expertise in any one given field, but they allow the students to explore whatever they want, so that they meet the minimal standards. And that's how I was able to sort of stay on at Harvard after finishing study and flourish because of the freedom they give. And there's no sort of say, this is the must study, so forth, because this is some other people studied before and proved to be great. So that the freedom is the most important. And you learn how to teach yourself about new things.
Let me just maybe continue with this line of question. The time that you were at Harvard, especially in the 1960s and
1958 to 2007, I don't know, that's my entire life was spent.
I'm thinking of the 60s and 70s in particular, as that 2 decades. Mm-hmm. You had, Harvard had you and it had Roger Brockett.
Yes.
The two of you. And it was really an amazing place that was competitive in terms of research with much larger programs.
Yes.
At MIT and elsewhere. And there were a lot of people that came through that were part of that mix briefly. There was David Jacobson and Peter Keynes,
yes,
many others. Can you just reflect on that and how you attracted these people and what it was like, the dynamics?
I really credit that to the freedom that Harvard environment provide. I mean, I had a great education at MIT, but certain things were already established and considered to be these things you must learn to study. And this stuff, I had a great education at MIT. I have no complaints. But MIT, the history of control theory knows, had great success during World War II and published this well-known series of books called Radiation Lab series books. But they got stuck in the old field. I remember when I was at MIT, I had a roommate. I won't mention names. He stayed on and finished a Ph.D. in control theory. But you never hear about him again because he got stuck working on the last paper in the old-fashioned control theory. And Rudolf Kalman, who got flunked out, completely revolutionized the field. And people who stay on at MIT did the last piece of work in the old theory, and didn't have the chance to see to take part in the new revolution. So
yeah, that reminds me of the famous saying that not only money corrupts, power corrupts, success also corrupts.
Absolutely.
So anyway, we also are very interested in you and your wife, the activities in the community of the Lexington and the Chinese community. What you want to
Yes,
clarify the question further?
Yeah. So hi, Larry, and this is mostly about your professional life, right? But this interview is taking place in Lexington. And this is where you and Sophia bought your first house, and one of your many ones, right? You had the only house and only this and that, right? So in Lexington, people know you, but really most know you as the husband of Sophia.
Absolutely.
And Sophia Ho got the King Award, which is basically a lifetime award for volunteers. She termed herself as a professional volunteer, right? But through her and you actually is also very active participating in all these town events, activities, and then in fact, I'm thinking about the local Chinese American, Chinese American Association of Lexington, right? The rejuvenation started in your house, when you and Sophia called us to order to do things. And then for the last, decades or so, you've been serving on the board and all of that. So can you say a bit about that part of your life experience here, how that impacted Lexington and beyond?
Yes, I always feel very proud that I'm introduced, at least in Lexington circles, as the husband of Sophia Ho, because she's really far better known. She sometimes jokingly calls herself the professional volunteer. She's on so many boards, served Lexington many ways, and got the highest award any citizen of Lexington can get, the so-called Golden King Award, which is given to a person at least 80 years old, have lived in Lexington at least 50 years, and by common consent or nomination, so forth, recognized, made the professional or devoted her contribution to Lexington town affairs. And she's, I think, the only Asian American so far that has received this award in 250 years of Lexington history.
So you've been emeritus. In fact, you had a very graceful, I would say, series of steps to retirement and emeritus status. And I just remember that I've admired you for many things, but I admired you in particular for your disciplined approach to retirement that you announced when you had decided you probably weren't going to try for any more grants.
Yeah, thank you very much for your kind words.
And then you announced your last student at Tsinghua, and then your last student at Harvard, and probably not in that order, but so just a very graceful disengagement. So how have you, apart from that and following that, what are you doing these days?
Oh, these days I actually could be considered as my third career now. Some of you know I write a blog, which is on the website of the Chinese Academy of Science and of Engineering, for which I'm a foreign member, elected foreign member. So to save time, I use their blog. They have a blog page, so it's very easy for me to write something and post it there. So I've been doing that since 2007, so it's 19 years now. Very rewarding. It's almost my third career, because I write basically about my own experience, and when the people ask me advice on something, I write an article, what I learned from this. And in the 19 years, I gathered about over 10 million readers, and really become very satisfying. Not everyone agree with me. They write back, argue with me, so forth, but at least I know some people are reading my work. And you've had a lot of people in 70 different countries reading my work. Sometimes they violently disagree with me, but then you are incentivized because you know people are reading it as an opinion of it. So that's basically what I do now in my retirement. I write about one article a week, and just on whatever I feel like. And people seem to enjoy it. In 70 different countries, I get feedback, so that's what I do now.
Mostly run-ins, nobody gets to the real output. They cut it short, because of time, money, everything, and in the life science, like animals, that they have to do ordinal optimization. Just go.
Yes.
But sometimes you make a mistake, sorry.
All I did is I developed a body of theoretical work to justify what good engineers, smart people do intuitively without being formal about it. Right. Now this way, putting a more firm foundation and let people develop more.
Right. So we already touched upon the other things that I was talking about with AI. Maybe you're not fully aware of that. Your teaching and your education, your textbook have a long-lasting impact on the current AI development. I told you sometimes, especially Yang LeCun, that his foundational paper on the in the 1988 about backpropagation explicitly wrote that by reading you and Bryson book, that he get enlightened to do this backpropagation and TPPVP is the same thing, so that's great. So let's move on to talk about you spend 5 decades in educational institute like Harvard and Tsinghua, no less than that. And so what's your reflection about your approach to guiding all these? I think 54 PhD students.
Yes, that's my lifetime output. 53 PhD students. And I think the one thing I reflect upon this, I feel is that it's really a matter of I teach some students. It's really a very, the process is an active collaboration. I think you experienced this yourself. When you were a PhD student with me, we meet at least once a week for very deep discussions. It's not really teaching, it's kind of active collaboration with me pushing you very hard and you pushing back. That's how we actually learn. And so the teaching, to me, is not so for one person pass on something to another. It's really to teach you, to let you learn how to learn by yourself. Because it's through this active discussing, me doing more pushing and you push back, then I feel both you and I feel you active, we both learned new things. So that's what I feel about teaching. It's a really very active form of collaboration.
One thing that I remember you keep telling us, is to learn how to speak and how to tell your idea in any amount of time to anybody. So I remember.
Yes, if you are forced, this is my own feeling, if you're forced to explain things to people, and so the other person can accept it and gain something, then you have to really understand the subject yourself. Don't accept any explanation. Subjects are very twisted and roundabout and doesn't give you any insight. That's why I said, Kalman's biggest invention, the Kalman filter. You can teach it in one course, give an hour lecture, a 10-minute summary, and 1-sentence summary. Both can be honest. By that time, you really understood.
Right.
And I think that's even quite common. I appreciate our collaboration.
Yes. I also still remember that when you were teaching error Horowitz the resource allocation problem.
Yes,
and, in basically 15 minutes, you give us, I still remember, and I tell other people about this lambda.
About what?
The lambda, the Lagrange multiply.
Okay.
Resource allocation program, and the constraint is basically the interest rate that the Federal Reserve is allowing every week, or every month. That was one variable decide all this work.
Yes, I always feel I won't give up on a subject until I thoroughly understand it and can explain it to men on the street what I'm doing and what I have done. And only there I say, okay, I understand the subject. I can leave it now. I'll go on to something else new.